Hey guys, welcome back to Algos Intent. We're going to now wrap up the summer 2020 volume with the following program. We're going to follow up from basic dynamic programming to have the final example of DP, a very common lead code interview question, also from Gail Lackman's cracking the coding interview, the paint fill problem, or also called the Canny dynamic programming problem. This is a very famous problem from AI, artificial intelligence, mainly coloring and also different forms of RGBA or red, green, blue, alpha coloring. In addition, we'll be able to wrap up Algos intended in the final episode, episode 10, which is going to be the MOB AHT, abstract hashing table, which is a form of ADT, an abstract data type. That finale will be put into two parts, which is a fairly long episode. I'm now very grateful to finally wrap up this Algos Intent playlist, and make sure you guys can subscribe. So yeah, as always, make sure to subscribe to the channel, Jason Liu. We're going to now basically try to use a very basic dynamic programming for Canny DP, which is also a subset of AI or artificial intelligence, and we're going to use it with the RGBA or the red, green, blue, and alpha colors. If you don't know what RGBA is, it's basically a form of like determining a color in terms of like general coloring. For example, if you have like an image of, I don't know, like a PNG or something, you get to break it down to pixels. So it basically becomes a pixelated type of photo. This is a very cool application of how we use graphic designs and like computer graphics to turn a dynamic programming problem into algorithm. So yeah, in this problem, we basically are given the following. You're given an image. It's a really crude drawing of a person. And within each image, you're basically also given an array of pixels for the person's, for example, for a person's head. So you have a person's head, you have the hair, and you're given the pixels in terms of rows by columns. This is very important interview. You do not use X and Y's variables because those will be confusing once you do some debugging on the paint fill application. The Canny DP, by the way, for this program is based on Canny Edge Detection, which is an AI concept of trying to determine what contours you have in a graphic. So this is an AI concept. If you want some more, I will add, if you want some more information about this Canny Edge Detection, I will add some links to the comment section. So yes, do not use X, Y as variables. So you're given the image, which is IMG. You're also given a set of pixels, P, and you're also given a value L, which, if you can guess from the RGBA value, is basically the alpha value of your pixel, the alpha value. This is very important because, as you know from if you ever played with Microsoft Paint or if you ever did any CSS coding with any colors, you'd understand that an alpha value L of 0 is basically transparent, while the alpha value L of 1 is opaque. This will become later as we determine the tonality of each color during the dynamic programming problem. Now let's get to the DP problem itself after having a basic introduction to graphics and AI. Of course, as a reminder for dynamic programming questions, we have the commandments, remember? So I'm gonna let you guys first pause and think about what were the commandments or steps of dynamic programming, which has been a while. It's been a while since we've done a DP problem for Algos Intent, but I would like to let people jog their memories a little bit. Okay, that's long enough of a pause. So of course, the first step would be a subproblem. That's something we should always be able to remember very quickly from top of our head. What's a subproblem? The second is the number of subproblems. The third, of course, will be the recursion or the Bellman equation. This one will be pretty simple compared to the other DPs because it's only going to have two variables in the runtime. And the fourth one, of course, is going to be your solution. And then finally, your runtime. I'm simplifying the DP a little bit because I noticed there's been a little bit of overlap between the final runtime and the final solution. And it actually technically is the same thing, except the final runtime is determined based on the number of subproblems times the recursion runtime. So you can basically mix it into one like general step for the DP algorithm. Now let's actually apply it to get the subproblem. So yeah, let's get through the problem entirely. So let's define a subproblem for this Canny Edge Detection dynamic programming. So conveniently, I'm going to name the subproblem as image. And image takes in 4 variables. R, C, which is row and column. The P, which is the pixel we're coloring. And L, which is the alpha value. So let me just quickly label these things. I'm sorry, that's not good. Oh, much better. Get in the habit of labeling your variables as well when you're coding these solutions. Good. So what does the image do? So this image is defined as the following. It's the usage. This is a very important word, usage. We determine how many colors we're using to do the Canny Edge detection. The more colors we use, the more precise our detection becomes. Of up to n, which means n total, of RGBA, which is red, green, blue, and alpha colors. We're not using just RGBA colors. Hashed, which we use a hashing set data type, into an array. Up to L, which means the number of transparent colors we have. Transparent or alpha value colors, or trans colors. That's the same thing. In the color paint. So this is going to be related to the paint fill problem on LeetCode. And here's where we finalize the subproblem, or this subproblem will be incomplete. At the starting point of P in each color and in paint fill of R times C row column. And that's it. That is your subproblem for the dynamic programming Canny Edge Detection. Now let's get to the number of subproblem and the recursion, which is pretty simple. So yeah, let's get through the number of subproblems, step 2. So ordinarily, when think about like Microsoft Paint or any like actual painting application in Microsoft Paint or even in Mac, some equivalent of that, how many colors do you usually have? Well, let's say you have, a really crude set of paints. So it's up to n, right? N is the total number of paints you have. So obviously this is a linear scan for all the paint colors you have in your Canny Edge Detection. So it's obviously ON. That's very straightforward. And it's up to the total RGBA colors in the paint fill for the Canny Edge Detection. Now, this is sounding really artsy, right? Well, you'd be surprised. This is one of the tougher interview questions that actually got as a practice OA for that of Wayfair and Amazon. Because these type of questions really make you think about dynamic programming. They're completely different, other than like what is the max of an array or what's the min of a tree. It'll be a more abstract way of thinking dynamic programming. Also, if you get into graphics, it'll be a nice head start for you. Finally, we get a really simple example of the recursion. So let's do the base cases first with recursion. Of course, if the pixel is just going to be 0, 0, we have XY coordinates. That's what I warned you, don't use XY for R and C because you get confused. So just have a pixel of 0, 0, XY coordinate. You'll have no fill. It means you basically leave it blank, it's white. Otherwise, if L of alpha, which is the alpha, is basically 0.0. You also basically do no fill because it's transparent. It's nothing. Otherwise, if L of alpha is 1, this is where it gets interesting. It's opaque. Then you fill the color of RGBA, whatever RGBA color you want for the Canny Edge Detection. Finally, if R, C is less than 0, you're out of bounds. You just don't do anything. The painting is basically blank. Your image is gone. Your image is just not going to happen. Now, let me get to part 2 of the recursion. This is where it gets a little bit fun. So for the Bellman equation, let me draw an example of how we're going to color this. So let's say you want to color, I don't know, the circle with red. So you want to color a circle red. Now with Canny Edge Detection, you just determine the edge of a circle, which is here. So you determine the edge of a circle using AI approaches that I have forgotten from BU undergrad. Sorry, determine edge of circle using Canny AI Edge Detection. I'm not using hands or anything fancy because that'll require a little bit of multivariate calculus, which is not necessary for any LeetCode interviews. Thank you. A shout out to my BU friend Alex Moisey for telling me how to do this while we are in Professor Becky's undergrad BU AI class. So yeah, it's really great to see AI and algo used together. It's fantastic. It's one of my favorite applications. This is how games also get built. Like if you ever think about how Pac-Man got built or Tetris got built, they use Canny detection to determine if your thing actually works or not. So anyway, you can go up here, you can go right here, down here, left here. And that will lend easily into the classic, most famous four-way. It's called the Four-Way Bellman. The reason why it's called a Four-Way Bellman equation is because you have either the image of R minus I, C, comma P, comma L, right? Or you have the image of R, C minus I, P, L. And I, by the way, is just the number of pixels off. So I is basically the number of pixels off from your current pixel. In case you want to like have a blank space or some sort of other like color in between. We don't get too much into that because that gets into a bit of MP hardness, which we have no time this summer to cover. So I'm sorry. MP stuff's gonna have to wait till next summer. It does get into MP coloring hardness for this problem. Or you could have the image of, well, you guessed it, right? If you have every positive, you have every negative. So you have R plus I, comma C, P, L. And then finally, image of R, C plus I, P, and L. And there you go. That is your, oh, careful. We got to do a max, right? So we got to do a max. Oh, sorry, this is getting really bad. It's getting really bad. So let me rewrite the Bellman equation. Once again, you can see this is getting to be a tougher DP to write down. It's easy to think about, but it's tougher to write down. So let me just write down quickly the max from I to N of this thing. And that will be equal to, yeah, I guessed it, the old subproblem. Image of good old R, comma C, comma P, comma L. There's your Bellman equation, backwards, but it still essentially is the thing you want. So let me quickly rewrite the Bellman while I figure out the runtime for a clearer understanding of it. So yeah, I conveniently rewrote the Bellman equation for you guys. Now it's a much nicer form, obviously. This is also a lesson in terms of neatness. So in this really small box, the time of recursion is pretty simple, right? It's basically up to the number of transparent colors you have, O of L. And then also, it's for the RGBA colors. So time of recursion is pretty simple. Final solution gets interesting. So for the final solution of the DP, final solution of the DP, it gets really, really interesting because you have to consider a bunch of edge cases. Well, you know what happens with math, right? What's this and that? It's called a plus minus symbol. And from arithmetic, we're going to use that now for advantage to write the final solution. It's really simple. So if we use that, it's much easier than writing this whole thing out 4 times in a row, which is going to waste a lot of time in interview and also just waste a lot of board space. So it's just going to be max of 1 to I to n of the image of R plus minus I, C plus minus I, because we're taking all 4 cases into account. And then P and then N, because N is the total number of transparent colors you can have, which means the absolute worst case, everything is transparent. Basically make a white painting, a white painting Canny Edge Detection, which is pretty interesting, but also pretty weird as well, as you could generally see. So let's finally get to the runtime, and let me show you a faster way to do this entire problem set with not even DP. So yes, let's finally go for the final runtime of the problem. So you have O, big O of something, right? So I say it's quadratic. Why is it quadratic? Because you have O of n for the total number of RGBA colors you have for the paint fill, for the Canny Edge Detection, whatever you call it. And you also times it by O of L because that's the number of transparent alpha colors you're going to have for the paint fill. And how do we know this? Well, this one's pretty simple. This is from the number of subproblems. And this is also from the recursion runtime. So that, in general, becomes O of NL, which is quadratic. And there we go, that is your runtime. To solve this problem entirely, without any dynamic programming, we introduced something called, wait for it, a coloring scheme, which is basically getting to something called 3 coloring. So let me show you a quick example of how we would solve this problem without any DP at all, but a little bit more advanced approaches. Let's say you have, again, this pixel of row and column. So the row and column is pretty simply defined as from 1 to n and columns 1 to n. So you have an n by n pixel to color using the Canny Edge Detection. And then using Canny Edge Detection, we can do the following. We can have a coloring scheme of sorry, that's not 6, that's a G. R, G, B, and A. For the simplest case, we do not care about A. A is just for extra stuff. So in this simpler solution, we just make transparency always equal to 0. So everything is opaque. So for this alternative approach, we consider 3 coloring. So if we color this part red, we can color any of the other parts red as well. But that's not necessarily true, because we also could color this part green and also color this part blue. So how do we solve all this mess? That's where we get into basically the concept of bipartite graphing. So bipartite graphing is another way, probably more efficient way of solving this problem. So bipartite graphing is pretty simple. You have 2 forms of a graph. You have basically 2 rows. You have a source and a sink. By the way, this is assuming you guys know what graph theory is. So you have S source nodes and T sink nodes with a super source and a super sink, S prime and T prime. So for our bipartite graph, we always color the nodes R, G, and B. R, G, and B. And this mapping is a many-to-many mapping because you can match anything to anything. So you just simply match these. However, for a bipartite graph, you may not do this. You may not match adjacent nodes on the same side. That is a no-no for bipartite matching. So how does this how is this problem get solved using bipartite matching? Well, we consider the following. Every time you connect the super source node to R, G, and B, you're essentially using one color. And when you're using one color, that means one thing. You can either reuse the other color, or you can change to a different color. And no matter how many times you reuse and change the color, you will always color up to n total pixels required for image. And that, ladies and gentlemen, is how we end the Canny Edge Detection. So this is Algos in 10, episode number 9 with Jason Liu. Make sure to subscribe and have a nice day, guys, and stay safe and wear a mask and social distance.